So our next speaker will be Dr. Jim Luckring. Dr. Luckring has 48 years of experience at NASA Langley Research Center, where he has directed and conducted aerodynamic research pertinent to a wide range of fixed-wing aircraft concepts. He's also made scientific contributions and provided research to numerous NATO activities over a 44-year period, and has 18 years of experience teaching graduate-level classes in aerodynamics, and is a co-author of over 100 scientific publications for numerous organizations and professional societies. His career has included extensive study of vortex flows, and he is a fellow of the Royal Aeronautical Society, and as well as an associate fellow of AIAA. Welcome to the stage, Jim.
Thank you, Eric. Number 2. So the title of my talk is Connecting System Design to Modeling and Simulation Capabilities. I want to acknowledge my co-authors, Scott Shaw from MBDA, William Overkampf from WL Overkampf Consulting, and Rick Graves from the United States Air Force Research Laboratory. And as Joe mentioned, this was one of the projects that we did in support of his AVT 297 program. Next chart. Oh, clicker. Where is the clicker? Oh, there it is. Thank you. There's the next chart. So the focus for this research, we decided to consider the question, how can modeling and simulation, M&S, better contribute to aircraft system design? And what we chose to do was to address a model validation hierarchy. And we actually developed a technique in the course of this NATO work. And I'll be talking about the creation of the model validation hierarchy. We'll be talking about prioritization within the model validation hierarchy. And the work involves both general principles and a practical example for a missile that I'll be showing you. Our approach extends the concepts that are discussed in the V&V book that Overkampf and Roy published. And we actually chose this as the approach. We thought it'd be interesting to take what they had there and see how far we could go with it for the interests of Joe's team. And what you'll be hearing about is our model validation hierarchies, something called a phenomena identification and ranking table, or PERT, as well as a gap analysis. Model validation hierarchies can serve as a bridge from systems engineering to modeling and simulation development. And this is shown in the cartoon of this, this pyramid that you see. The top of the pyramid is a complete operating system. The bottom of the pyramid is where the flow physics are. And the question is, how do you link this all up? So the validation hierarchy is one way to do this, where the linkage between the system design and the modeling and simulation is established. Of equal and possibly more importance is the prioritization of simulation capability development, and that's based on the system performance needs. So we're not putting these together for everything and anything that might ever happen. This is targeted work based on some system need that's got to be addressed, usually on a fixed time frame and budget. This shows the structure of the model validation hierarchy that we came up with, and there are 3 parts. The first part is a systems architecture perspective. This follows a traditional breakdown of systems engineering for a complexity decomposition, systems, subsystems, and so forth. The important thing for this work also is that the system design requirements are specified in the systems architecture portion of this model validation hierarchy. A new concept that we developed was what we call a transition tier, and the transition tier transforms the thinking in this work from a systems architecture perspective to a physics taxonomy perspective. And this is where mathematical modeling is introduced to the hierarchy. Below the transition tier is a physics taxonomy perspective. This is where the modeling and simulation features are specified, And this is where the physics and phenomenological decomposition occurs, from very complex physics all the way down to fundamental unit problems at the base. Some attributes of this work. The hierarchy is developed. I'm having a little bit of a hard time reading these slides, so I apologize if I'm having to stare at the floor. The hierarchy is developed to address systems design requirements. So this is targeted work, as I said. The systems architecture and M&S linkages are established at the top. The systems design requirements are, the focus is established at the top. Moving down the hierarchy corresponds to a deconstruction of element complexity. The sections of the hierarchy, they can have multiple tiers. The number of tiers is arbitrary. So you set that based on the problem that you happen to be working. And each tier can have multiple elements and sub-elements. And you see some examples there of a couple elements on a tier, or one element that has a sub-element structure. And we found that to be very advantageous to acknowledge just the way the physics are, and also to flatten the hierarchy. A final point that's very important is that this approach is modular. The hierarchy is reusable and adaptable to support new future requirements. It's put together, targeted based on some current requirement, but it can grow. You don't have to throw away what you've done. And in this regard, it can become a strategic asset, we feel, for system and interests and for future modifications. Let's see, there we go. So let's talk a little bit about conceptually the notional structure of the hierarchy. Starting at the top, this shows the systems architecture. At the beginning, at the highest level, would be the systems architecture tier, which is really it's usually a system of systems. We're going to look at how we drill down in the hierarchy, and I'm highlighting one element there with the blue outline for further analysis. There can be any number of intermediate system tiers where you go from things like the full systems, looking at the system 2. We identify some number of subsystems. This could continue on down as needed into components following traditional systems engineering thinking. But there will be a lowest systems architecture tier, and this will usually be smaller than a smaller number of tiers than you see in full systems engineering treatment, because the lowest tier is just what you need on that tier to introduce modeling. Because since this is a M&S, a model validation hierarchy. This slide shows the notional construct of the transition tier. I'm highlighting one of the elements from the lowest systems architecture tier. At the next tier down, you see the transition tier, and this is where we show the element 1 modeling. And in this example, we allow for the possibility of there being, in this case, 3 disciplines that warrant separate modelings. Maybe one is fluid mechanics and one is solid mechanics. Each element would have its element modeling entry on the transition tier. And then from the transition tier, if we look at the one modeling element that is circled there, I think that's discipline 2, we would start a physics taxonomy. I show the highest physics taxonomy tier. This would be where the most complex physics would reside for that particular sub-element on the transition tier. And there would be a taxonomy for each one of the entries on the transition tier. Turning to the physics taxonomy notional structure at the bottom of the hierarchy, I've repeated the highest physics taxonomy tier. You can think of the most complex flows or the most complex electromagnetic interactions. And we can pick one of those elements, and that will be primed. That's demonstrated now at an intermediate physics taxonomy tier. This is where you start the physics-based deconstruction of the complex physics into intermediate level physics. There will be a number of these tiers which are problem dependent. when you finally get to the lowest physics taxonomy tier, this is where your unit problems would show up. From my perspective, being an aerodynamicist, the unit problems, this is where we see things like a boundary layer on a flat plate, maybe with an oblique shock reflecting, things of that nature. The key thing is that all of this is connected explicitly from the full system down to the unit problems in the vertical direction through the model validation hierarchy. There's another new concept that we developed in the course of doing this work in support of Joe's project, and that's the coupling element. Everybody knows that systems and subsystems are coupled, and really it's the coupled issues that can be quite challenging in this business of making viable airframes. For the model validation hierarchy, we introduced this notion of a coupling concept, and it's shown as the diamond on the transition tier. And it's shown that it occurs between two element modelings. The one on the left has its physics taxonomy, the one on the right has its physics taxonomy, and the coupled modeling element would have its own physics taxonomy. And we've assessed this in many different ways in the NATO work. One way to think about this, even though this is a notional slide, if you thought of element 1 being an airframe, and you have airframe modeling in the transition tier, if element 2 were propulsion, you would have propulsion modeling on the right, and what would be in the middle is the propulsion airframe interaction modeling, PAI. PAI does specialized testing, they have specialized codes, they're going to have their own physics taxonomy, and it's connected in the lateral direction for a coupling element. Okay, so let's look at an example. I think it helps to consider something in our case that's actually flying and has some specific physics on it. And the example we chose was a ground-based air defense system, GBADS. And for a GBADS system, what that typically is comprised of is a launch system, command and control system, a detection system, and the missile system. And so it makes sense at the top, at the system of systems level, to simply identify those four. That is the top of the hierarchy for a GBAD system. Now what we're going to do is highlight, we're going to drill down following the missile system, and you could drill down any of these. We chose to drill down on this path, and you'll see aerodynamics in a minute, and that's only because that's where the expertise of the co-authors and myself reside. If we want to look at what would be below the missile system, we have a second tier in the systems architecture, which is comprised of missile subsystems. The photo or the sketch at the bottom comes from MBDA. It shows a representative missile concept with the typical subsystems that you see there. And you've got GN&C, warhead, airframe, propulsion, and the seeker. And so that constitutes the tier 2 in the systems architecture. Now in systems engineering, you would keep going, basically following the geometry and the parts. And at some point, when you got to the bottom of that type of thinking, you've got washers, and rivet counts, and things of that nature. We don't need to go that far. And actually, for a model validation hierarchy, you don't want to go that far. You only want to go down as far as you need to introduce the mathematical modeling. And for this example, which is going to be based on aerodynamics, supersonic maneuver, this is all the further you need to go, because we're going to introduce modeling on the transition tier in the next chart, and we're going to focus on the missile. Oops, I'm sorry, wrong button. Okay, so for the missile, when we go to the transition tier, for the airframe. For the airframe, when we go to the transition tier, we're going to introduce airframe modeling. In this example, we have two disciplines to consider: aerodynamic modeling and structures modeling. This is fluid mechanics and solid mechanics. They'll each have their own physics taxonomy, and I'll show you a little bit about the aerodynamic modeling. Here I've repeated the transition tier at the top with aerodynamic modeling, and I'm showing you what a physics taxonomy could look like for this application. For very complex flows, it's common practice in the aerodynamics community to consider the fundamental structures that we see in flows. Shock waves, vortices, boundary layers, wakes, and jets. So we just chose that as the organizing principle for the complex flows for the aerodynamic modeling. It's also common to have interests in unit interactions, how vortices interact with boundary layers, and so forth. So I'm showing that as a second application. And notionally, you could think of the interest, since this work is all targeted, the interest is going to be, say, supersonic maneuver. And you know the way missiles are, and if you remember the picture, there's vortices all over the place. And they play a key role in how the vehicle maneuvers. So we chose that as an example. The unit interactions, below those you can typically find canonical cases, and so on and so forth. An important thing here, though, is that we've actually put this physics taxonomy together based on the way aerodynamicists work. And with this approach to a model validation hierarchy, you can do that. We put together a structures modeling physics taxonomy, and it'll be in the NATO reporting. And that's put together the way the structures discipline works. So this approach embraces the way the different discipline areas do their job. And we think that's a real strength of what we've done here. Everybody gets to work the way they're accustomed to working, but we have an approach that gets that all connected in the context of the model validation hierarchy and up to system performance needs. Here's the example of coupling between the airframe modeling sub-elements. We've been focused on the airframe modeling. You see the aero modeling on the left. You see the structures modeling on the right. Each one of those would have their own physics taxonomy, as I've just mentioned. The diamond in this case shows the coupling between aerodynamics and structures, which we all know for this room, this is where aeroelasticity fits. Aeroelasticity has its own discipline. It's going to have its own physics taxonomy, perhaps distinguishing static from dynamic. There'd be other ways to do it. Specialized facilities, codes that are developed to address aeroelasticity. The point, though, is that the coupling element is what enables these coupled interests to fit into this concept of a model validation hierarchy. And we've worked this from all different levels. In the NATO report, we even have an example of coupling that originates from the system of systems level. I think it's between the launcher and the missile itself. And you've got particulates and all sorts of different physics that shows up. It doesn't matter. So far, it seems like this new concept of the coupling element, it just works. Okay, so that's enough about the hierarchy itself. You've put this hierarchy together, targeted, to address some system performance need that a program manager, say, is responsible for responding to. The next step since you have the hierarchy, is to prioritize what's in it, so that you end up doing what seems to be what will be the best work to address whatever the need is. We've talked about creating the hierarchy itself. The prioritization here I'm showing has 4 elements. You create the hierarchy based on system needs. We next have created something that we call a hierarchy element prioritization, or HELP table. And this is where prioritization is done based on the importance of a particular validation hierarchy element to some system response quantity. Next, there's the creation of a gap analysis. And this is where we establish the validation status for the various prioritized elements. And there can be a lot of them. So what you have to do is the final step is to prioritize those gaps. Which ones are most important to work for the question that's on the table? And I'm going to summarize these a little bit. For the HELP table, this shares a common philosophy with a prior process that's known as the Phenomena Identification and Ranking Table, or a PERT. PERTs have been around a long time, and it's been my experience that not a lot of people in our business, in the aero business, are aware of this. PERTs actually came out of the nuclear power safety side of the house. They use M&S to help assure the safety of nuclear power plants, and they developed something called a PERT to help guide their analysis and pick out what parts of their M&S are most important. We found that we could leverage almost all of the PERT for our interests in terms of a model validation hierarchy. And there are 4 key features to the help table. An environment and scenario that are under analysis are stipulated. For us, you could think of the environment as, say, being normal operating conditions. And for the scenario, I'd like you to think about supersonic maneuver of this missile. You stipulate whatever it is that you're working on. There's a list of the hierarchy elements for assessment that are germane to that particular environment and scenario. And they're listed there as, what is it, A through F. Those would be like vortex flows or shock waves or things like that. Next, the system response quantities of interest are going across the top, SRQ 1, 2, 3, for a supersonic maneuver of a missile. That might be lift, pitching moment, and rolling moment, let's say. And then there's an outcome from of an importance assessment. Are these particular elements very important, moderately important, or not very important to whatever the item is at hand? And then with a simple color coding there. And this results in a ranking of the importance of the various hierarchy elements with respect to an SRQ. Now, one way to look at that is shown on this chart. This chart shows the model validation hierarchy for the GBADS example that we worked as part of the NATO project. It's for the missile system. And in this display, the sunburst on the left, it shows the missile system in the center. The next ring out would be the subsystems. So as you go out in the circle, you're moving down the hierarchy, and you end up with the unit problems all the way out at the fringes. This will be assembled for the environment A, the nominal operations. The scenario is supersonic maneuver. And this, notionally, this would be what it could look like for, say, rolling moment coefficient. And what you find, and this is a complete hierarchy that we put together for the NATO project. What you find, first of all, right away, is that there are a lot of elements that you can rule out. They're important in the hierarchy, but they're not important to this particular scenario, environment, and SRQ. And then we've colored the ones based on the help outcome to start to show where the important stuff is. And the important stuff is red. And I've got a blow up there of the hierarchy, so you can see that there's aerodynamic modeling, and there are the vortices, the vortex-vortex interactions. And in this notional idea, we end up with things like vortex breakdown, and I think it's vortex asymmetry that are considered to be of high importance to the concern regarding those supersonic rolling moment behaviors of this missile. So you can get a pretty quick snapshot of what the help table looks like. And you can see that out of what could be a lot of unit problems, you can narrow this down pretty quick to find the ones that seem to be important. Next, the gap analysis is done. This also shares common philosophy with the prior process. The fellows that did the PERT analysis did a gap analysis. And we found once again that we could leverage just about all of their work. And it's been around for a while. There are just a few changes that we had to make to plug in the model validation hierarchy to their thinking. 5 key features. Each environment and scenario is stipulated across the top. I meant the supersonic maneuver. This is for SRQ3, say the rolling moment coefficient. There's been a down select for the subset of the model validation hierarchy elements from the help table, so we only have 4 shown here. And then going across the top are the standard items that we need to assess the status of, the modeling, verification, validation, UQ. And here we're assessing the, what do we know about our capability? Is it unacceptable, unknown, or acceptable? And this starts to give you, for the targeted flow physics, what are the aspects of the simulation that you need to go after? Do you just need to get some verification done? Do you need to do a validation test? Maybe everything's okay and you just need to do some UQ. So this identifies the M&S capability weaknesses. And then, of course, the next step is closing those gaps. These gap findings, the analysis identifies the high priority M&S elements, and the M&S elements themselves connect all the way back up to the top to the system design requirements. And at least in my way of thinking, this is the point that you would probably report back to your program manager with what you've done, what you found. There are going to be groups of SMEs, subject matter experts, that have helped you get to this point. And you can actually lay the whole thing out so that collectively you make a decision of what work is the most important to do. How does the schedule fit with the program needs? And do we have the money to do the right job? That can be a collective decision. With the decisions made, gap closure work is pretty much the standard stuff. Model validation experiments, improved numerical simulations, etc. And the gap closure impacts, the first one there is, I would also say, is fairly common. Gap closure provides the enhanced M&S confidence at the level of the hierarchy that you worked at. Maybe that goes without saying, but I think you need to say it. The other thing, though, is that the model validation hierarchy could broaden the impact of this gap closure work that you did. Down at the bottom, the physics taxonomy, it's got a lot of closely related physics right around the particular topic that you used. So you could be able to do a more well thought out assessment of the new technology, maybe a better turbulence model. You could look for changes in emergent properties. You could do a much more informed physics assessment of the new work. At the top end, the systems architecture could enable impact assessments of closely related design options, which is more of a practical configuro level assessment of whatever this new turbulence model does. And it seemed to us, at least, that this could really enhance the understanding of what you did in this targeted piece of validation work. So I think we can get more bang for the buck by exploiting the hierarchy in the ways I've described. Okay, concluding remarks. This has been a significant extension to the model validation hierarchy that we developed. Bill was on our team. When you go back and if you read his book and you go back to the earlier charts, the basic ideas were there. But we've taken this quite a bit farther than what he published and others. It's built on the general concept of deconstruction of complex systems. This allows system design requirements to be systematically connected with physics-based model validation features. And I think that's really important. You want to do this work on things that count, or things that are important to the overall system and to the program managers that you work with. It connects systems architecture and physics taxonomy through a transition tier. That's something new. It accommodates coupling effects. That's also something new. It accommodates discipline-specific conventions and practices, and I think that's critical. If you didn't do that, I don't think it would be used. And this is robust. It can be applied to air, land, sea. I should have had space on their systems, diverse physics. I talk in terms of fluid mechanics and aerodynamics, but you can talk about anything. We could be doing electromagnetics, or you could be doing space radiation on a capsule. It doesn't matter. And to repeat a key point, this approach is modular. You start out putting a model validation hierarchy together to solve a specific interest for a specific problem, specific program, specific program manager, but you can reuse what you've got. and you can just keep building it. The hierarchy can be reused again and again to meet new system design requirements. You can leverage what you've already got. So the model validation hierarchy can become a strategic asset if you choose to view it that way. Number two, the hierarchies can be exploited using this, as we call it, a help and gap analysis. The help table provides a structured means to rank the importance of model validation hierarchy elements based on system design requirements, and the gap analysis provides a structured means for prioritizing help table elements for the targeted M&S improvements. Everything is traceable, 100% traceable, and you can explain to anyone who's interested in the work you're doing what you've got and how you got it and who helped get it. The integrated model validation hierarchy, help, and gap processes are generally applicable to any type of engineering system. They establish rigorous and traceable analysis driven by system design requirements. And they lay a firm foundation for improved M&S-based decision-making on systems. I'm going to go like 1 minute over because I can't leave acknowledgments out. You don't do work in a vacuum, and we've had diverse sponsorship for this work that's gone on for about 5 years. You see 2 NASA programs, the Transformable Tools and Technologies, Advanced Air Transport Systems. We had a research branch. We got support from the Air Force and from the NATO Science and Technology Organization. The call-outs have to be, the most important one is to T-Cubed, as we call it. T-Cubed helped fund Bill Overkampf. They supported my time to do this research, and they supported my ability to stand here, to come to this meeting and tell you about this work. Without T-Cubed, this would not have existed, and I appreciate the support that we got through them very, very much. Money and manpower is always tough. The Air Force Research Lab also funded Bill. We've had critical reviews from Jack Bennick on this work. And of course, the NATO STO organization enabled the scientific collaboration for this project. So thank you. I'm about 1 minute 15 over, but I appreciate it.
Thank you, Jim. So because we're going to have a panel session right after this, if you wouldn't mind to hold your questions till that point, I'm going to go ahead and introduce our last speaker as Dr. Dimitri Mavris. He's the Regents Professor in the Aerospace Department at Georgia Tech and head of the Aerospace Design Laboratory there. He's involved in a few activities in aerospace, and I think, and in his spare time, he's going to be the incoming president of ICAS. So, Dimitri.
Thank you. Well, I hope you're all enjoying this. It was a labor of about 3 years of planning and a lot of philosophical arguments as to which direction to take. And as Joe described, there were swim lanes that everybody was supposed to go down the path, but the beams were allowed to cross, not like in Ghostbusters, okay? So we were allowed to interface and exchange ideas. And to some extent, the portion that I have here today is tackling some of those elements and follows what Jim was saying about the taxonomy. We came to a very similar conclusion that indeed the physics layer was needed, for the transition. And the path that I'm going to take in this presentation is to show you an example that perhaps can drive home some of those issues. So the portion of the problem that we are responsible for was directly linked to a military transport aircraft compared to the missile design that Jim was talking about. And we wanted to showcase the process, describing a process for identifying critical databases for use in model validation. So obviously we're interested in vehicles like the one depicted over there, kind of like a futuristic CX type of configuration for air mobility. Obviously that's the goal, to demonstrate the process. We had to take a step back and maybe use something that data was available, B was kind of military, C was supported by NATO AVT, and so forth. And as the diagram is depicted at the bottom, you have this combination between what computational analysis I have to do, what experiments I might have to perform, and the like. So that need for a framework was extremely important. So everything that we did was actually trying to build this capability. And then since we had to take a systems level perspective, and the reason for that is very obvious, sometimes something seems to be very important until you roll it up to the level of consequence, only to realize that it was insignificant. So at that point, the higher fidelity you build in those areas, the more complicated you make the problem. And if you think of design, that's why we have conceptual design, preliminary design, and detailed design. A rib can easily have 1 million different permutations of just the rib itself, okay? But I don't want to do that for every part, so I'm abstracting it as I'm moving up. So for instance, for a vehicle like this, I might be interested in, does it meet its range requirements? Is it free of flutter in the operational envelope, like Rob was presenting this morning with the VN diagram? Does it meet the takeoff and field length requirements and the like? So our portion of the exercise was the development and implementation of a methodology that is very similar to what Jim was presenting, that will contribute to the identification, quantification, and reduction, kind of like the UQ that was identified today by the certification by analysis as a desired state. And in this case, what we're doing is we're trying to reduce epistemic uncertainty. If the term is unfamiliar to you, uncertainty usually is classified under aleatory and epistemic. Aleatory is non-reducible, so usually you're talking about robust design and things of that nature. Epistemic uncertainty is more along the lines that it's lack of knowledge, which means that the more I study the problem, the more iterations I do, the higher fidelity I go, eventually I have a chance of actually shrinking that distribution and de-risking a given problem. So the approach that we took was founded in a model-based systems engineering approach. So of course, to do model-based, you have to do systems engineering. And of course, all that is under the overall category of a model-based engineering. It tries to draw on established engineering principles, because if they're not, then people most likely will not use it. It will be too foreign to the processes that they use. And then it extends them with insights with contemporary modeling practices that, again, for people in the field are not particularly new, but if you have never seen those before, they might look novel. And it yields guidelines that may be applied in a wide variety of multidisciplinary contexts. So reduction in uncertainty associated with computational model predictions for the purpose of reducing cycle time, reducing costly design iterations, and de-risking the overall development of these new concepts. So for this presentation, I'm going to break it down into 4 portions. The decomposition of the problem, very similar to the ontology. And in fact, it was identified this morning as a needed element, those ontologies. The development of the models for the purpose of our exercise, and then how we propagate those uncertainties for the purpose of identifying which uncertainties are the key ones to work on. And if I know that, that immediately leads into what experiments I have to perform or higher fidelity analysis for the purpose of reducing those epistemic uncertainties. So again, I'm not going to read all those charts word to word, but it's there for your reference. All those, whether it's the FAA or EASA, in this case, qualification for military aircraft, they're documents that kind of describe the necessary steps that one has to take to demonstrate that something is safe enough. So in this case, I'm using an example, the ASIP process for certification of aircraft. This is the Aircraft Structural Integrity Program. So there is a document that describes the entire process. So from that document, I'm taking out, the phases, the primary task that one has to perform to demonstrate that the vehicle is meeting the various criteria. So for each and every one of those things, I can either go and do the actual testing, or I can do some kind of an analysis. And before I commit to anything like this, I need to know whether that the physics of the problem are well understood in order for me to do the analysis and de-risk the program. And it's only when I feel that the analysis is not founded in the physics of the problem, I'm start deciding if I'm going to go to higher fidelity or highest fidelity, or if I'm going to do any physical tests. So the idea there is to be motivated by this context. I mentioned systems engineering. For those of you who have never done any work in systems engineering, think of it like I have a set of requirements, and I need to flow them down and allocate them. So in this case, the same approach can be used where the allocation is along the lines of what analysis has to be performed, at what level, what tools, how much fidelity I want to build in those tools, and so forth. And that allocation implies that I have some kind of a quantitative approach on trading options. I can do it this way or that way, and in the end, I can determine which direction to take. The functional decomposition is also there because in some cases, I haven't done the problem, so I don't know how to physically decompose it. It's not a derivative. Maybe I haven't done this before. So it's not uncommon, especially when people claim that they're innovating, to do a functional decomposition and then synthesize to come up with architectures that will solve that problem. So we left it open enough. As I said, it's a framework. A framework implies that the answer in the end is not a specific outcome or result. It is a place that has all the necessary hooks to do some use cases. The next person comes along, adds more use cases, and eventually you have a library that can do all of the above. And then the element of the systems engineering, you have the traditional V, which is very good for product development. But the way it's depicted over here on the top, it has a series of those Vs that implies that before I even go to commit into one thing that ultimately I'm going to build and test, I'll probably have done thousands, hundreds of thousands of other paper designs, if you like, computational model designs, for the purpose of de-risking it. So by the time I end up committing to doing something specific, I don't want to have an oops moment that I have to go back and scrap it. And of course, again, Rob today and some of the other presenters presented the modern version of the V in the form of the Boeing diamond that kind of shows both the traditional V at the bottom and the computational version of it. And in fact, when you look this animated, it kind of shows vertically and horizontally how those verifications and validations are happening. Now, Joe did mention, as he was giving a quick prelude of how the various teams were proceeding, our decomposition is very similar to Jim's. It's, of course, viewed a little bit different here in this diagram. But you always start with what it is that you're trying to do, identification of the requirements from the documents that I was just referring to. For example, for the example that we were talking, that was a relevant document. And then in our case, we're going to break it down into a mission decomposition. Tell me what mission you're trying to perform and at what mission segment you are. That's one piece of information that you need. And then the second one is what exactly you're trying to do, so I can decompose the functions. And from there, let's move into the architecture, and I'm going to do a physical decomposition. And then the combination of the physics that you're trying to capture for the operating conditions, and of course, what part of the airplane, is it the whole airplane, is it just the wing, is it the engine, the fuselage, that will actually decide what type of modeling I'm going to do. If you think of your modeling, you always need some geometry, right? And you need conditions and so forth. The intent is to link it directly to those elements. So just showing you side by side the two perspectives. In the function decomposition, you have an arrangement of functions, and there are sub-functions and interfaces. So of course, we decompose this for the C5. At the bottom, you see a mission profile. So the idea is, again, you're moving segment by segment, and you say, what am I doing at this step? What am I doing at this step? And the like. And then on the right-hand side, similar to what Jim was showing, we're seeing a decomposition of a vehicle. In this case, it has the elements of a transport cargo type of military asset. So it looks like a C5. So then you go into the overall decomposition of the problem, similar to the taxonomy that was shown. We also have a demarcation point that you say, at some point, I did my decomposition a la systems engineering. Now I need to be thinking of the process, how will I analyze those things? So what you see over there at the bottom is physics that you're trying to capture as they pertain to specific element. And then one level below, you have the disciplinary methods that you might be using. And one level below that, every entity will have codified those into tools. So they will have a specific code that they prefer depending on the level of sophistication and the physics that someone is wanting to use. So just to put it into use here, for the C5 model, we're going to pick up a baseline C5. It's the C5A. It's a little bit older generation C5. And we're going to model it. And within that modeling, we're going to build an environment for the purpose of quantifying uncertainties, propagating them. And we're going to try to tackle what happens if you have couplings, like Jim was saying. If you have a coupling between error and structures, what will that do to the answer? What does that do to my remaining uncertainty and the like? And the intent there, again, is to try things of mixed fidelity modeling, kind of like saying if I had this coupled or not, if I include this analysis or not, do I have ways of quantifying what that impact will be? So you start again in putting together a multidisciplinary analysis environment, starting with the mission, the geometry, and the various disciplines that we tackled over here. In principle, the environment was integrated, so we could have done propulsion and other things. In this case, the propulsion is, in this case, uncoupled. Of course, the airplane needs an engine, so there is the engine's model for the C5. And then we have the aero structures, and the aeroelasticity is that coupling between the two. So the coupling between aero structures gives us that aeroelasticity. And we're trying to reduce the overall uncertainty in the system performance, and we want to see exactly how that happened, where did it come from, what were the contributions, and the like. So this n-squared diagram that we had before manifests itself into an integrated environment. In this case, we didn't have to start from scratch and stitch all our codes together. It so happens that our lab, we have done this activity in support of other programs within the Air Force and NASA. The environment is called RAID, and it has a little depiction over there. Some elements are commercially available tools, others are homemade tools. You have a geometry that you obviously interface with all the tools. And in this case, I wouldn't say that this is high fidelity. It's like mid-fidelity, just for demonstration purposes. The idea is that when you see something that you don't believe that is capturing the physics accurately, you drop down one level below in terms of sophistication. And then that same n-squared diagram is presented here as an XDSM, a design structure matrix, kind of showing the information that is being exchanged between the various modules. In this case, is the uncoupled one, where the air and the structures are not coupled together. And in the next one, they're actually coupled together, so you're accounting for the deflections and so forth. So it was done both ways, and then in the end, we're going to try to see the impact that those things had. Then we went through a little verification just to make sure that the models were working properly. So you have the wing box deflection for, in this case, 1G and 2.25 Gs. Then we did a design of experiments trying different conditions, tried the aeroelastic versus non-aeroelastic. So once we get to a point that we felt that we had enough of a model, we started now structuring the framework to assess uncertainty. So you're trying to find at what places do you envision epistemic uncertainty to enter. So early on, before you commit to the analysis, you can very easily change the ranges of the error, if you like, from that analysis to see how sensitive the outcome will be, and that will give you some guidance on how to proceed. So in trying to formulate it this way, we wanted to decide what the uncertainty parameters will be. Usually they're disciplinary metrics, and needed a way of sampling it. So we're driving it towards doing some kind of a probabilistic analysis on this one. And because these analyses tend to be rather cumbersome, it takes quite a bit of time to run, you want to speed up those processes. So the borrowed thing here is that you run a design of experiments around the integrated environment to actually generate the necessary data to surrogate it, create surrogate models, either neural nets or some technique like this. And then those surrogates are so fast to use that you can manipulate them very quickly to do either inverse design problems or to do probabilistics. And the attempt over here was to have an environment that the team can come together, that someone can make a decision on the fly and they can see how the results are differing. And also sometimes because of the objectives, there's not one objective, there are multiple objectives, and the weightings are not a priori known to the designer. You almost want to leave that degree of freedom to a review team that is going to decide, the emphasis that they want to put to the various criteria. So it was built with that mentality in mind, that some kind of an interactive parametric environment might be desired. So that's a visual walkthrough of how this is working. Here is our XDSM. So I want to perform studies and by sampling the range within which I'm varying a given process. The process takes a few hours to complete. So if I had 1,000 samples per uncertainty factor, that would be about 2 years. Of course, that's on a specific machine. If I had a cluster or a cloud computing or whatever, it might be different. But just for reference purposes, it kind of gives you a perspective. And in many cases, 1,000 samples might be too little. If I'm interested in things in the tails of distributions, I might need hundreds of thousands or a million type of calculations. So the idea is to propagate them through, and every time I have a feedback, now I have a probability on top of a probability. But the intent is at every level to figure out how much variability I'm getting from that step. So when Joe and Jim mentioned about rolling it up to the system level, that's exactly what it is. I want to get to the point of consequence to find if those things really matter. And if they don't matter, even though I might have a 10% uncertainty, at the time I get to the top, it's 1%. Maybe I don't care about that 10%. I want to care for the ones that a small perturbation leads to great results. So we did a design of experiments around that problem to speed up those processes. So the Monte Carlo is actually done on surrogates rather than on the actual codes. So imagine now design of experiments around the entire analysis. And then in this case, we tried a neural net representation for every response that we were tracking and every constraint that we were tracking. And then, of course, when I have that capability, I can very quickly do a Monte Carlo and speed up those processes. So now I have the framework kind of run, and I have the surrogates so I can operate on, so what kinds of results I can get. Well, for starters, I can do parametric sensitivity. So in this case, the horizontal rows are different things that I'm tracking, and I can do this at every level. In fact, we're interlinking them so I can cascade them, so I can look at them at every level. And then at the bottom, I have key parameters. In this case, these are things that they might be, these are not geometries anymore, but these are disciplinary metrics that might have a little bit of a play. And right now I'm showing it to you as a PowerPoint slide, but in reality this is something you put up on your laptop or you're projecting on a screen. And those hairlines, if you touch them and move them, it automatically updates the numbers on the vertical axis. So it's like a calculator. And then of course it shows me the sensitivity. And as I'm doing the sensitivity, it automatically says that this is true when all the other variables are fixed at a given value. You fix the other values, those things move up and down, orient. The first one has a little wiggle, automatically tells me that something in my modeling didn't go well. So it's also a debugging tool of sorts. Someone mentioned today in all the certification, I think it was Rob, that when you see some of your data, you realize that something wasn't working right. So this is, again, another byproduct of the formulation. It's helping me in debugging those things. So I have predicted results. The blue numbers show the uncertainty bound around the current point. So in a sense, they're like 3 lines on top of each other. Sometimes they have error bars. It shows me how much of an error was introduced by the fact that I was creating a surrogate of a model, like a model of a model. And then the blue bands indicate this and the slope of each plot shows a positive or a negative trend, and as well as a relative importance. So once I have this formulation now, I can drop down into a gallery of distributions. So in this case, it shows a uniform distribution, meaning that I'm a little bit agnostic as to whether there is a central tendency or a bias in the shape function. So uniform distribution is almost like a random number generator within that range. And then literally you run 10,000 cases just by snapping your finger, and you get the probability distributions on the right-hand side. So that's a sense of how much uncertainty, in this case, for this example, one thing is varying, the other things are fixed at values. And then I can come in and say, okay, if it's not a uniform distribution, what is it? Do I have any prior knowledge of this thing from prior investigations? And you change on the fly what that shape function is going to be. And of course, in this case, we're just doing 1-to-1. I can change the values of the other ones to bracket the whole thing. If the uncertainties are too wide, then it can be adjusted based on the subject matter expertise. And if that indeed is the range, then I know that that variable has a big impact and I have to pay attention, or I have to have ways of reducing it. Compared to another one, for instance, where in this case the range was narrowed. And of course, as you're narrowing the range, it also narrows the distribution at the top level. And again, this is just one variable. In reality, I have to do this for each and every one of those variables, and eventually have to do it for all of them, and then quantify the results associated with that formulation, okay? So right now I'm building it up one by one, but of course I would not be doing it that way. In this specific case, it turns out that the uncertainty in the Young's modulus and the material densities were showing the biggest impact, and we wanted to pay attention to that. I also have the ability of changing values of fixed uncertainties and seeing how much of an impact they have. So you see I'm doing it by changing the value. It changes the distribution, shifts the trends. So it's an interface for me, right, to try to understand things that traditionally I was just too slow to do. And this is now an example where all the distributions are varied at the same time, and I'm documenting on the right-hand side how much variability I'm getting from this presentation, from this representation. Okay, so that's the impact of the total uncertainty. Okay, so at that point now, I can extract this information and I can send it over for further statistical analysis. Since I have equations, I can even solve this numerically. In the next step is to do it with the addition of a coupling. So we're going to do this stereoelastic analysis. So if you look at the very front, the very first column, it has a categorical variable that tags between doing a rigid or an aeroelastic formulation. So when you move it from one to the other, loads all the equations associated with that mode. And of course, if I do it that way, it could be viewed like I added fidelity, if you like, or I believed that the phenomenon was worth capturing, and I didn't take the shortcut, and I did it the right way. So if I tag between the two, I see the impact of before and after, if you like, with and without. And if I was to superimpose them, I can see if there is a shift in the distribution or the variability has narrowed in the amount of variability. Okay, so I have this ability of moving in all directions and trying all these different perspectives. Now, we did advertise that eventually we want to propagate this all the way to the top level. So right now we have gone to the lowest level for this demonstration. So right now all those things are feeding into the wing, and then you're trying to figure out what that distribution is. So you're doing this, decoupled, and then you're doing it coupled, so you can see back and forth what impact it has at that level. There is a shift and there is some kind of a distribution, and now you need to propagate it one level above. So in this case, we linked it directly with an aircraft sizing and synthesis tool. So it's a propulsion plus mission plus the overall behavior of the vehicle. So now the rows are actually top-level requirements, and you're trying to see what this impact will be at that level. So again, similar format, sensitivities. Those two things are interlinked. So as you're maneuvering and manipulating them, they cascade through, so you can very easily see the impact that it has at every level. So just like before, now I have distributions, not at the wing level, but all the way at the vehicle level for the things that I track. So in a sense, now I'm going from the wing directly into the top level, and some of the things that we were tracking would be the range, the takeoff field length, and things of that nature. And of course, you can pick a point, and just like we did before, you can show the impact of aeroelastic versus rigid aero, not just at the wing, but all the way to the top at the things that you track. If the variability is too much, of course, you keep on going. So that would be a depiction of that cascading and that interlinkage. So when I decide what it is that I want to go do next, I'm always looking at what these distributions will look like. I can do an analysis of variance to see within the ranges that I'm varying who are the biggest contributors. And in this case, we did it both for the decoupled and the aeroelasticity one, and you can see the relevance or the importance was different between the two. And that gives me some guidance. And now I can turn around and give guidance to my experimenters of what it is that I'm looking for. Because if you think of a TRL doesn't improve the value of the metric. It actually shrinks its distribution, so it's a de-risking activity. So you're trying to figure out what experiment they need to perform in order for them to zero in on a specific uncertainty. So in closing, we try to capture, a methodology on how critical uncertainties in these design simulations can be combined, increase the risk on new aircraft programs, and create critical decision points. We're trying to reduce all those, and we're trying to avoid physical experiments. So we're trying to develop an environment that will allow us to give some guidance into the process. If at the end the physics are well understood, I'm going to rely more and more on computational methods, and that hopefully will go very much in line with what the certification by analysis friends of ours were talking this morning. In the case where the physics are not well understood, then I have to go off now and guide the process. And because I cannot afford to do every test, I'm going to try to zero in on the identification of the most critical uncertainties and build upon them. And the framework is driven by the fact that I can speed up processes now. And if I can run many, many cases and I can collect all my assumptions, my inputs and the outputs, then I don't have inputs and outputs anymore. I have vectors of data, and I can very easily solve inverse problems. Okay. So with that, I'm going to thank you for your attention, and I think we're going to be able to take questions in the panel, right?
Yes. So if we can transition to our panel setup, and then there are questions in the audience. If you could please make sure you direct them to the speaker, or if it's to the entire panel, that's fine as well. You're right, it is really hard to see. So any questions from the audience at this point? So I will go ahead and ask, so given what you guys have seen thus far, what do you think the next steps are to make this more viable for application?
From my perspective, having now seen how the other teams progressed, some synthesis is probably the immediate lowest hanging fruit, kind of harmonize and demonstrate step by step how those things all come together. It was almost like a formative phase. To me, that would be the lowest hanging fruit to do next.
I think from my perspective, and at the moment this is speaking from the project that I described, I know we've had an interest in finding maybe a practical application, somebody that would actually try to do this, the validation hierarchy that we laid out, and that was not on the team, so you get this kind of independent assessment of what works and what doesn't work. What sort of things did we miss in assembling this thinking for the NATO project? So, and at the moment there are conversations with the Air Force Research Lab directly along these lines about trying to find some sort of an application project that they could try with a little bit of guidance from us.
And also the decompositions, they were not as easy as they look. You almost need a subject matter expert in that domain. So the more disciplines you bring in, you almost need a team of experts to decompose more and more and more. It was a lot harder than it looked,
So I think a couple things. I think that it would be good to take one or two of these decompositions and actually show it, build it out. Because Jim and I think Dimitri and I think that the 297 community talked about, reusing these. So you put together, maybe it's fairly easy. When I say it's easy, it means I'm assigning that to somebody else to do. It's fairly easy for somebody to take this and apply it to a single discipline. So, we had a lot of aerodynamicists that could break down the aerodynamics, get a structural modeler to break down the structures, then work with an aeroelastician, and let's do that coupling between the two and break those. But do it for a simple problem so we have a good example. That is then the starting point to work on a more complicated problem. In innovation, one of the most critical things is the first adopter. So we have the people on this team, all these teams, that have put together these thoughts and these ideas and these processes. We need, as Jim said, that early adopter, that person outside of us to start picking it up, because that's critical for this to become something that is used elsewhere. And so we need to be working to find who that early adopter would be and trying to get that early adopter to pick this up and start working from where we are.
So you definitely need subject matter experts, and the reason why we try to link it to systems engineering and MBSE is that the more you bring the various disciplines together, the number of requirements will explode. It will be an enormous number of requirements, right? And those requirements need to be flowed down, need to be allocated, which means trades need to be performed. So I think this was a pilot, right, to take it to the next level. It only grows in complexity, right?
So you said that it definitely it looks easier than it actually was. So what would you say your biggest lesson learned from this would be?
Well, from my perspective, it was interesting how people who are all in the same field decomposed it differently or looked at it differently. And there was almost like one layer was missing until, in the end, both groups came to the realization that there is almost like a need for a transition, from the one way of looking at it to the way you're going to model it. And once that piece fell in place, I think things started clicking again. But for instance, when you try to take it to another domain, let's say we decided to do aerostructures and then couple aeroelasticity, then you realize that the aerodynamicists saw the problem one way, the structures people another way. There were even arguments if aeroelasticity is actually its own discipline rather than a coupling, which of course if you have an aeroelastician in the audience, they get exception to that fact because to them that is a discipline, right? But in reality, it's almost like taking every coupling, and because it was significant and because it's difficult to do, it became its own discipline, right? So you almost have expertise in those levels, and someone from the outside, it's almost like reinventing the wheel, right? And in the cases where someone is an expert, you're forcing them to think of the problem a little bit differently. So you would think that that part was easy, but that was not straightforward. It took time for everybody to get on the same way of thinking of the problem, from my perspective. Yeah.
Eric, your question was lessons learned?
What do you think the biggest lesson you learned out of this process was?
I'm not sure about the biggest, but I will say I found it interesting how much work it is to develop some of these ideas. But it takes time, and you've got to make, you really have to be able to make a number of mistakes along the way. We've ended up with what we think is something that could be useful. But man, you should see how many versions of that ended up on the floor week after week. And I think the having an entity such as it was the STO in this case, and having this 3 to 4 years to work this was necessary. I just don't think we could have accomplished what I like to think we did quickly or on the fly or with only a couple minds, having the diversity of opinion and the debate for that extended period I think was really valuable and something that you have to set up to do. It's not always easy, in this environment with, changing priorities and funding constraints and all that jazz. But if we can't work on this type of 3 to 5 year frame, I don't think we're going to necessarily get the products we need.
It was the consensus building for sure.
Yeah.
You can always come up with ideas, but to have others consent to it, that takes an effort. And the other one is, for most of us, this was volunteer work, right? So you will think that will be a hindrance, but in reality, it was very rewarding because you have people from different domains that they're all truly are trying to solve the problem, like it's almost like a thought experiment. It starts like a thought experiment. And I've always thought that endeavors like this one, and I saw the same thing with the certification by analysis within AIAA, people put a lot of their free time. This was not a contract for them. They put free time to figure out how to solve the problem. And there were some very nice discussions, spirited discussions at times, to get to a point of convincing or not convincing somebody.
So I think the lesson learned is, the one I'm going to take away from it, is how important it was to have the right community working on it. I think we benefited tremendously from having the international community working on it. If we had put together a small team working on it, I don't think we would have, if we had, for example, chosen any one of those teams and said, go work this problem, I don't think we would have ended up where we were. I think that every person that was part of that team brought something important to the discussion. Mm-hmm. And there was a lot of, we had twice annually meetings that we all got together. And once we'd gotten to the point where we were in teams and beginning to develop, each team presented their work. And so there was this cross-fertilization of ideas. And sometimes in those meetings, people were saying, no, that's wrong. And you might see them 6 months back, coming back and going, okay, now we see the benefit of that. And so that exchange of ideas and that multiple teams and the breadth of the international community, following up what Jim said, I think that the STO gave us a good umbrella to do this development in. We could do it in other formats too, but I think that it was a very good design for us working this kind of a problem. Mm-hmm. And like both Jim and Dimitri have said, it took time. It took time to identify these problems and work down a path and identify that was a dead end. And then come back and try to figure out, okay, now how do we go down a path that's not a dead end? And we went down a lot of dead ends.
And I don't know if it came across when Joe was presenting it that we tried to see different perspectives. So there was the air or transport versus the missile. There was another one for naval and so forth. It's just that those didn't get as far along. But the idea was to see how different vehicles and so forth see the world, because sometimes those communities have evolved differently. They have different principles of how they see things. And I think for the missile team, having Oberkampf, he was good because he came in from Sandia. He had the perspective of what is happening in the nuclear side. And those guys that don't believe in approximating anything. It's hardcore modeling, simulation. There is no testing left anymore. They're not allowed to do that. He had, of course, the book in the verification and validation for CFD. So there was firepower there, in terms of perspectives. So it was not just a pure aerodynamics perspective. It was, like in our case, we came in from the system perspective down, so it was a top-down. I think the other team was more bottom-up. In the end, both of them ended up having a continuum. It didn't start from that point. I think over time, both teams came to a solution that is not that far apart, actually. Mm-hmm. Yeah. There's a question there. There's a microphone coming.
Very good, thank you. So it sounds to me like there was two separate approaches here that need to be reconciled. Is that a true statement?
I don't know that they need to be reconciled yet.
Okay.
They're two slightly different approaches, and I think that we need to work with them a little bit more and understand them. They share more in common than they are different, but I think that we need to work through them and understand. We didn't set off trying to come up with one hierarchy to rule them all. We were trying to allow freedom and flexibility for people to find different approaches. And there are at least 3 different approaches that are shown here. Well, 2 were shown here. There's at least a 3rd one in the group that was doing Missile Team 1. That's a little different approach. And I think that we need some further time to work through that and see whether or not they need to be reconciled or if they stand distinct.
Okay, so I would say that work, so it's incomplete, I guess, at the moment, right? You're still working through coming up with perhaps a single proposed approach that, say, a team like Cert by Analysis could use, right, to make decisions. So, once that is done, it seems like the next step would be to put training material together to help people understand how to apply the technology, right, to solve problems. Have you guys thought about that aspect of it?
That's my retirement plan, Jeff.
I think, Jeff, the plan wasn't that in the end, as Joe said, there would be one thing. It was broken down on purpose to see different perspectives. But as I said, obviously the next step will be, okay, now if you were to unify something, right, for a purpose of a given problem, then you can cherry pick elements and how to combine them,
And we had even viewed that, at least with these 2 approaches or products, as at times we saw it as complementary work. There were things we knew that Dimitri was doing that we didn't bother doing as much of that, if you will, because there was enough things that we were interested in doing. So I think thinking of these as complementary is part of the story in this NATO project.
Exactly. The composition that they came up with is what eventually we will use anyway. It's just that they were working on that part. So when I say about slapping them together, is you can take one approach and following it all the way to the end, right? So.
And Jeff, back to your training materials question, I anticipate that we will see an update to Oberkamp's book, where he will take lessons learned from this activity and roll them into his book. So there's a training material that already exists to a large extent that will be updated with some additional information that came out of this activity.
I'm sorry, Joe, go ahead.
But as far as putting together training material, we haven't actually actively talked about that recently, at least.
I mentioned at some time there is interest at the Air Force Research Lab at applying some of this work that I was reporting to some of their airframe interests. And if that should end up happening, it's going to force some level of training material topic, because part of the purpose of that, beyond the fact that there's some people that think it might help them with product development, the other purpose is that getting people that were not part of the development team to try to use this. First of all, they've got to be guided and explain what it is that they're doing. And then there's got to be a way to capture, the problems and issues, the things that we missed, with that type of application assessment. You really want people that are going to bust it. They're going to find things that this particular team missed. And all of that's going to feed some sort of maybe for lack of a better term, an ad hoc set of training guidelines, something of that ilk. We'll just have to see what comes out. Bennick is one of the key points of contact for that activity, Jack Bennick.
I think there's a question over there. Yeah.
You hear me? Yeah. Magnus Ek, VTI. I have a question for Jim. In the PERT and in the gap analysis, you do importance ranking with different colors. Could you propose or comment on objective but still feasible methods of actually doing this importance ranking?
Comment on what was this, objective but feasible?
Yeah, objective methods for doing the importance ranking. What should be red and what should be green and so on.
So you mean objective rather than subjective, rather than subject matter?
Quantitative, quantifiable, quantitative way?
Yeah, basically methods on how to do the importance ranking.
I think the honest answer to your question would have to be no, I can't comment on that. I know that there are some things out there, but I don't feel schooled enough at this moment sitting here to give you a good answer.
I can give you a shot at this, okay. So from that matrix, the quantitative approach that was showing was mapping against some of those boxes, okay. So if I don't have the ability to do the analysis, I go to the subject matter experts, and that's what was depicted over there. But you can take the same construct now, and in the cases where you can do analysis, you can identify how sensitive that outcome is or how accurate. So that analysis of variance that it was showing with and without accounting for the coupling, what impact it has, that is a way of quantifying that impact. And then you can either put it in a more value type, or you can do it colors again. But when you don't have the analytical ways, you do subject matters. If you have the ability, you can do quantitative ways. Yeah.
Okay, thank you.
So if I can add, I think this is where the two primary methods we're showing here actually have a lot of complementary aspects to them, where Dimitri was showing a little bit more of a subjective approach, quantitative approach to being able to rank importance. And this is where we really need to take a look now and bring those methods together, if possible, and take the strengths of each of them and have a nice combination.
Yeah, before you can do any analysis, there is a subject matter expert portion that has to happen.
Yeah.
Very similar to what Jim was presenting, right? Like, what physics am I trying to capture? Someone has to know what logic has gone into the tools that they have, right? Can this physical phenomena be captured by whatever it is that I'm talking about? There is no code that is going to do that, right? So someone has to provide the logic. And then over time, I have a library and says, I'm going to pick this, I'm going to pick this, combine it, create an MDA environment. Mm-hmm. Yeah, so those two are always going to work together. It's not either or, There's a question way up there,
This is Pradeep Raj from Virginia Tech. I think the question, Joe, I've been wondering about, if you reflect on how you came up with the CRM for the drag prediction workshop. So I'm wondering if the people not involved in that exercise, if you ask them that we want to have a model and that has a certain CL, whatever kind of conditions that you are expecting it to perform. And then you say, okay, now find out where all these uncertainties in the analysis that you can come up with, say, for example, the work that Dimitri was talking about. And the same kind of construct from the missile team, that would work too. I think the construct would work, in my opinion. And it would be interesting to see the decision that you made. Were there any better way you could have done that? So I'm just curious, I'm just thinking out loud about kind of the challenge that you went through and the expense of doing that, what kind of data you really need in order to validate the fact that I want a certain L over D and a certain CL, or those kinds of things, which would obviously be applicable to a real design exercise. Yeah. Thanks.
So I wasn't part of the team that came up with the original CRM design. Was associated with those people very closely, though. So I'll kind of talk more from the juncture flow perspective. But that's where the reusability of this kind of a hierarchical structure, I think, really benefits, because you identify as you've built this structure up over time, you've added more and more features. You've added more and more things that you've seen in different configurations. And so when you look at a new configuration, then you've got all of these things where you've identified, oh, here's a case where we had this side-of-body separation. Maybe we have side-of-body separation that we're going to have on this case. And so we need to be aware of that. We need to be careful of that. We're not so worried about having a large vortex. We're not horribly worried about the side-of-body horseshoe vortex. We actually were worried about that, and we designed it out. We tried to design that so that side-of-body horseshoe vortex was pushed away from the interaction region, and I think we succeeded in that, because if it was close, it was going to impact that interaction. And so we knew some of these things, and so we used that as our design process. One of the benefits of having a formal hierarchy is that you are instantiating knowledge from many people over many years. And it's not just a list of boxes on a diagram. It needs to be some examples. It needs to be some data. Maybe there are even some estimating parameters. If your boundary layer is in this condition, if your boundary layer growth is in this condition, if you see this kind of a pressure gradient, then these are things that you're concerned about. You know, obvious things are Mach number that tell you you're going to be worried about shocks. Obvious things are sharp edges that are going to tell you you're going to have a vortex here. That sharp edge is going to be a place where you're going to have separation. And so, you know, this is a way to try to encompass that knowledge and provide that as a starting point for somebody when they look at a new problem, to say, oh, I never thought about a vortex-vortex interaction. And here I can see geometrically that I've got a chine with a sharp edge, and both of those are going to have vortices, and there are going to be conditions where those are going to be interacting, and I need to be dealing with it.
Thank you. And just what comes to mind are the couple of problems that we have had. For example, C-130J had the stall roll-off problem, F-18, as you know, the wing rock problem. Right. I just wonder if there is a way those could have been prevented if we, not that that was the first time it ever happened, those kinds of things we have known about. The question is, how do we know that the design that I have will or will not suffer from that? So I wonder the proper hierarchy and some kind of validation through some kind of analysis would have helped to reduce the chances of having that in the flight test. So that's kind of benefit that you could derive from it, from the just the framework, apart from the validation that you're talking about. So that could be an interesting extension to that. I don't know if that makes any sense, but this is the first time I heard about it, so I'm just thinking out loud on that. But you might have some opinions on it. I mean, it's the whole panel. Thank you.
I think it makes perfect sense. Mm-hmm. And I think that the whole objective is to identify that these things might be an issue. If you know that they might be an issue, you can do additional analysis, you can propose specific experiments, you can look at how this was handled in the past and see what conditions there are. And so the validation hierarchy is the art of what's possible, maybe. And so maybe it can help guide you to find those things and then look for, hey, we need to be careful about this. We need to go do additional analysis. Maybe we go through a port chart to identify this is a critical thing. Maybe we go through Dimitri's systems analysis to go through and identify this. And maybe we can do some underlying analysis to say, yeah, I think this is going to be there, or no, this doesn't appear to be there. Thoughts?
Yeah.
on the panel?
Well, the hierarchy can help also into kind of zone into what some of the underlying physics really are for something like a wing drop. You know, what was causing that. And once if you think you've start to get your arms around that, that's where you could start to do whatever the verification or validation work would be to elevate the capability of your tools, your simulation tools. And it does, you know, whether it's RANS or wall modeled LES, it doesn't really matter. It probably will be the latter. But if you have confidence that, you know, your technique, the scale resolving technique, if you can actually show that it's actually nailing some of the physics that were critical to why wing drop showed up on F-18, you've got a tool that could help prevent that. Well, you've got higher confidence that the tool might help prevent it in a future design activity.
And Pradik, you know, we had a lot of discussions about this, you know, like if you are a fundamental analyst, right, aerodynamicist and so forth, you will want to do very unit level experiments, like you're isolating an effect. And in one of the slides that Jim had, you know, you start showing more complex phenomena, how they work with each other and the like. So sometimes it's kind of hard to find funding for things like that. Most of the experimentation that is done in these days is analysis has yielded a given configuration, and we're analyzing that configuration almost like a point solution. But if you're truly trying to understand the physics of the problem, you have to parametrically vary a lot of things, including the geometry, to truly understand it. And sometimes there is no budget for that, or sometimes there is the perception that we have been doing this for 100 years. What is left to do at that fundamental level of understanding? And there is more of a chance to find money for a real development of a program. But by definition, that thing is a point solution with all these effects masked in whatever it is that it was, right?
All right, well, I think we have reached our time limit for today. I want to thank the panel for your presentations and for your discussion. Thank you to the audience for your questions, and have a great evening.
Thank you for attending. Yeah.
Thank you, Eric.
Thank you, everybody.